There's a number that should change the way you think about your house. On a clear summer afternoon, your attic is sitting between 120 and 150 degrees Fahrenheit, sometimes higher. The roof above you has been absorbing sunlight for 6, 8, 10 hours, and now it is radiating every joule of that absorbed energy straight down, into the air, into every surface, into the floor of your attic, which happens to be the ceiling of your bedroom. That is not a slow leak. That is a furnace running directly above where you sleep. And the strangest part of this particular story is not the temperature, it's what happens next. A single layer of aluminum foil, properly installed, reduces the heat pouring through that ceiling by 49.8%, almost exactly half. The number comes from Oak Ridge National Laboratory, 2013, measured in a controlled side-by-side study inside a large-scale climate simulator. Most homes in America don't have it. If that gap between what's been proven and what gets built is the kind of thing you cannot let go of, subscribe now, because that gap is exactly what this channel exists to open. The material costs around $30 for a starter roll, a weekend afternoon to install, no contractor, no permits, no structural changes. And the reason you've never heard this from a builder, a contractor, or an energy auditor is a story worth knowing. The technology did not come from a hardware store, it came from space. In 1955, a mechanical engineer named Clark E. Beck, working at Wright-Patterson Air Force Base in Dayton, Ohio, was handed a problem with no clean solution. NASA needed to protect astronauts during spacewalks from temperature swings ranging from 249 degrees Fahrenheit above zero to 245 below, a 494-degree spread across a single outing. Without covering them in 7 feet of material, the suit had to fit, it had to flex, it had to weigh almost nothing. Beck's answer was not insulation in any traditional sense. It was a reflective aluminum layer, thin enough to fold into a shirt pocket, light enough to feel like nothing, that reflected 95% of incoming radiant energy before it ever reached the person wearing it. No mass, no thickness, no chemistry, just a surface that refused to absorb what was aimed at it. The physics had been documented a century earlier by a Parisian physicist named Jean-Claude Eugène Peclet, who, in the 1850s, had spent years studying surfaces that reflect rather than absorb radiant heat. Beck was not discovering the principle. He was engineering it for the harshest thermal environment a human being had ever entered. It kept Apollo astronauts working in short sleeves inside the command module. It flew on virtually every NASA mission that followed. In 1996, the Space Foundation inducted it into the Space Technology Hall of Fame. NASA placed the technology in the public domain, and for a time the trajectory looked like it should. Companies began adapting the technology for homes. A company called Infra Insulation, Inc., founded in New York City in 1945 by a man named Alexander Schwartz, became the largest manufacturer of reflective foil insulation in the country. Magazine advertisements showed ordinary homeowners installing it with a staple gun. Millions of square feet went into American homes. Engineers specified it in designs. The physics worked exactly as Peclet said it would, and Beck had proven it could. Then Alexander Schwartz died. And the product that had been going into American homes for 15 years simply ceased to be available on the market by 1965. No safety concern was raised. No scientific paper came out against it. No building code rejected it. A company was gone, and no one filled the vacuum for a decade. What filled it instead was a product that an $18.5 billion industry had every incentive to sell, patent, and protect. And that industry made a very deliberate decision about how the conversation around insulation would be structured going forward. They made R value the metric that mattered. R value measures resistance to conductive heat, the kind that moves through solid material the way a hot spoon warms your hand. Fiberglass handles conduction. It earns its place on the chart. Radiant barriers don't have an R value. They were never designed to resist conduction. They reflect radiation, an entirely different thermal pathway. By defining the entire conversation around R value, the traditional insulation industry created a framework in which their product always appears on the chart, and the competing technology does not appear at all. When someone asks, what's the R value of that foil? And the answer is, it doesn't have one. The sale is over before the physics begins. That became the standard. And once a standard is written into building codes, into contractor training, into the language of every home inspection report, it tends to stay there. Here is what is actually happening inside that attic. The heat coming through your roof on a summer afternoon is not primarily conductive. It is radiant. Infrared energy, the same wavelength your skin detects when you hold your hand near a lit burner without touching it, doesn't travel through material. It crosses open space at the speed of light and then gets absorbed by whatever surface it strikes on the other side. Your fiberglass, your ceiling joists, your drywall. Every surface in that attic has an emittance rating of approximately 0.90, meaning they absorb 90% of everything that arrives. They don't slow it, they don't deflect it. They receive it completely, warm up, and then radiate downward again into your living space. And your air conditioner spends the next 6 hours compensating for an oven it was never powerful enough to beat. Aluminum foil has an admittance of 0.03 to 0.10. Where a standard building surface absorbs 90% of incoming radiant energy, foil absorbs 3 to 10% and reflects the rest back upward before it ever reaches the floor below. The air gap between the foil and the surface beneath it is not optional. Without it, the material just conducts, passing heat from surface to surface like everything else in the attic. But with that open space, with the reflective side facing down into the air, something fundamentally different happens. The hot roof deck radiates downward. The barrier reflects most of that energy back toward where it came from. The attic floor never receives the full load. The insulation, the ductwork, the conditioned air, all of it operates from a cooler starting point. That is not a marginal difference. That is a reversal of the relationship. Back in 2013, researchers Sam Shrestha, William Miller, and Andre Desjardins at Oak Ridge National Laboratory built 4 identical attic configurations inside a large-scale climate simulator and ran them under controlled summer conditions. One attic had no radiant barrier. 3 did, each in a different configuration. The most effective setup: low emissivity foil stapled to the underside of the roof rafters, reduced heat flow through that ceiling by 49.8% compared to the unprotected control. Not a projection. A measurement in a federal research facility under controlled conditions. A second study, conducted at Appalachian State University under a DOE Building America grant, translated that heat reduction to your actual cooling system. Peak attic temperature dropped by 23 degrees Fahrenheit in homes with barriers installed. Air conditioning runtime during the 7 highest heat hours of the day fell by 20%. And the efficiency of cooled air moving through attic ductwork improved by 57%. That last figure is the one most people don't expect. In hot climate states, across Texas, Florida, Arizona, the Gulf Coast, the Southeast, the majority of homes run their HVAC ducts through the attic. When that attic sits at 145 degrees, those ducts are running through a space actively working against them. The air arriving at your registers is warmer than it should be. Your system runs longer. It wears out years ahead of schedule. A cooler attic is not just a more comfortable attic. It is a more efficient mechanical system from the moment the compressor kicks on. The Florida Solar Energy Center measured radiant barriers dropping attic temperatures by 30 to 40 degrees Fahrenheit during peak summer conditions. Not outdoor temperature, attic temperature. If yours reaches 145 in August, the barrier brings it somewhere between 105 and 115. The U.S. Department of Energy translates this into 5 to 10% savings on annual cooling costs in warm, sunny climates. In a home spending $250 a month keeping rooms cool through June, July, August, and September, that is 4 months of real money every season without fail. And unlike your ductwork, your air handler, or your aging insulation, the foil doesn't break, doesn't degrade, doesn't need replacement. It sits there doing its job. Here is what you need to do. Find rolled reflective foil radiant barrier. Perforated, not solid, because moisture must be able to move through it. At most major home improvement stores, a starter roll costs around $30, covering a full attic of 1,500 square feet in material runs between $150 and $400. A contractor quote for spray foam or blown-in insulation covering the same area typically runs between $1,500 and $4,000. That is not a marginal price difference. Go up on a cool morning before the heat has had time to build. Start at the ridge and work toward the eaves. Staple the foil to the underside of your roof rafters, not the attic floor, not the joists below, the underside of the rafters, reflective side facing down. Let it sag slightly between staple points. You need at least a 1-inch air gap between the foil and the roof deck above it. That gap is not a detail. Without it, the mechanism fails. Keep the eave vents and ridge vents completely clear. Overlap seams by 2 to 3 inches. Stay away from bare electrical wiring. That is the whole job. If you press your hand near the installed foil on a hot afternoon and feel noticeably less radiant warmth coming off it than from the exposed roof deck nearby, that is the reflection working. You are feeling, in the heat radiating from your palm, the difference between a surface that absorbs 90% and one that absorbs 3%. That is not a product. That is Pecklate's physics, operating exactly as he described it in Paris in 1850, exactly as Beck engineered it for the moon in 1955, exactly as Oak Ridge measured it in Tennessee in 2013. Most homes still don't have it. There's a particular frustration in that sentence, not at homeowners who have no obvious reason to know any of this when the building industry never made it a standard. The frustration is at the distance between what a federal laboratory measured and what a contractor recommends, between what a NASA engineer proved in 1955 and what a new home built last year contains. Beck solved the thermal problem for the moon. The technology came back to Earth. The national labs confirmed it. The Department of Energy endorsed it. The Space Foundation put it in its Hall of Fame. And the answer to what is in your attic right now is, for the overwhelming majority of American homes, fiberglass on the floor, open air above it, and a roof deck that absorbs everything the sun sends down. Your attic is proof of it. If this is the kind of gap you want to keep pulling at, the space between what works and what gets built, and who decided which one your house would get, survive better is where we pull. Because the question underneath all of this is not about foil. It is not even about heat. The question is, who wrote the rules about what goes inside your house? And what did they decide was too inconvenient to include?